Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be talking about energy level diagrams with respect to molecular orbitals. So let's get into this. So energy level diagrams, what are they? So if we go back to atomic orbitals for a moment, so here you see that we have our energy level diagram when we're talking about atomic orbitals. And so here, let me move this over a little bit. So yeah, oops, 3D, that was off screen. That's a little bit better. Okay, so here's the atomic orbitals, and we learned that the atomic orbitals fill up for atoms, right? Based upon certain principles and rules, right? So remember the Aufbau principle. Electrons like to be the lowest energy possible, so they're going to start down at the 1s. You're going to fill in the 1s first, and then fill in the 2s, and then the 2p, and so on. So you're filling from lowest energy possible up to the next higher energy levels with all the electrons that you have available to you in that particular atom. Remember the Pauli exclusion principle. You can only have 2 electrons in an orbital maximum, and both electrons must have opposite spins. One has to be spin up, the other has to be spin down. And then you have Hund's rule, where if you have equal energy orbitals, you're going to fill in one at a time, spin up, before you start pairing them up with spin down. So if you have the 2p, you have fill them in one at a time with one electron. So you have one spin up, spin up, spin up, and then you start pairing them with spin down to fill up the rest of the orbitals. So just like in the atoms that you have, where you fill in an orbital diagram or an energy level diagram, you also will do the same thing with molecular orbitals. So let me go bring your attention to this. So this is an energy level diagram, an orbital, molecular orbital diagram for filling in molecular orbitals with your valence electrons. So what you'll see here, so we have a 1s orbital on this hydrogen. So we're looking at what are called homonuclear molecules. Those are molecules that have the same atom bonded together. So hydrogen is the simplest one. So we have 2 hydrogen atoms bonding together. So the way you draw the orbital diagram or the energy level diagram for molecular orbitals is you have the unhybridized or the non-combined parent atomic orbitals on the outside. So here we have hydrogen with AO atomic orbital. So we have the 1s from this hydrogen. And on this side, we have the other hydrogen atomic orbital, 1s. And both of them have 1 electron. So we have the parent atomic orbitals on the outside. Those are going to combine. Remember the linear combination of atomic orbitals? We add those together and we get our molecular orbitals from that. And remember, you always get the same number of molecular orbitals from the whatever number of atomic orbitals you combine. So here we're combining 2 atomic orbitals, so we get 2 molecular orbitals out. And so again, remember, we're treating the orbitals as wave functions. We're treating the electrons as waves. So when they interact with each other, they can interact either constructively or destructively. If they interact constructively, then you get bonding, a bonding molecular orbital. If they interact destructively, you can get an anti-bonding orbital here. So here, when they add together, if it's constructive, that's going to be lower energy. So you get lower energy molecular orbital here, and then you get a higher energy orbital over here due to destructive interference or combining destructively. So in constructive interference lowers energy, destructive interference raises energy. I'll talk more about that in just a moment. Okay, so remember, you get your 1s orbitals. These are going to be from your s orbitals, are going to form sigma 1s molecular orbital. And again, that's going to be a molecular orbital along the internuclear axis. We have two nuclei here. You'll notice that the molecular orbital, the sigma 1s, is lower in energy than these two parent uh, atomic orbitals. So the molecular orbital is lower in energy. Why? Because the electrons have a lower energy when they are shared between two positive nuclei. So when the nuclei are sharing the electrons, that lowers energy, and so they want to have that lower energy. And so what's going to happen is that the two electrons that are at this energy level, notice that this energy is higher, they're going to prefer to be at the lower energy. So these two valence electrons from the atoms are now going to be added to the molecular orbitals. So here we have one molecular orbital, here we have another molecular orbital. So just like we filled in the atomic orbitals here, we're going to we're going to combine the electrons from the two atoms, and we're going to fill in the molecular orbitals according to the same principles, right? So we're going to start at the lowest energy levels first, Aufbau principle, and we're going to fill in each molecular orbital with two electrons most, and they have to have opposite spin. So that's the Pauli exclusion principle. And if you have two molecular orbitals that are at the same energy level, then you would fill in one at a time before pairing them up with electrons, thus using Hund's rule. So this is a very simple molecule. So we don't have a very complex molecular orbital diagram. We only have two molecular orbitals. We have two electrons. So those are going to come down here, fill in here with the two electrons, and then that's all we have. So you'll notice here that the two electrons are now at a lower energy level. This means that having the electrons separated into two different separate atoms is less favorable than having the atoms combined into a molecule. So because the electrons prefer to have a lower energy, they're going to come down and they're going to form a molecular orbital. So the molecular orbital is going to be favorable. So forming the molecule between the two separate atoms is going to be more favorable than having the atoms separate. So this indicates that the H2 molecule is possible. And so we know that already, because we know that we have hydrogen atoms that are bonded together in diatomic molecules for hydrogen. Okay, so that's for this orbital here. We don't have any more electrons, so we can't put any electrons up here. Otherwise, we would put them in here. If I had 4 more electrons, or if I had 3 electrons, the third electron I would put up into the anti-bonding molecular orbital. So you'll notice that the anti-bonding molecular orbital has a higher energy. Well, why is that? A couple of reasons. You'll see that there's a nodal plane here. So this nodal plane indicates where there is 0 probability of finding the electron. And so that indicates that the electrons are not going to be shared equally, or not going to be shared by the atoms in the molecule. They're not going to spend time with both of the nuclei in the atoms, or for the atoms, right? So because of that, they're going to share. They're going to only be associated with one atom at a time, not at the same time. So remember, for molecular orbitals, here for this one, the electrons are shared, or they spend time, or they're um, shared between the two nuclei. So they're kind of belonging to both nuclei. Here, the electron is only spending time on one nucleus, or it's going to the other nucleus, but it's not at both nuclei at the same time. And so therefore it's going to have a higher energy. Also, the electrons are farther from the nucleus in the anti-bonding orbital compared to what they would be in the parent uh, atomic orbitals. So here, for the 1s, the electrons are actually closer to the nucleus, meaning then they're going to have lower energy, because the closer you get to the nucleus, the less energy you have. So they're able to be closer to the nucleus in the 1s orbitals, the atomic orbitals, compared to the 1s, the sigma 1s star antibonding molecular orbital. So the antibonding molecular orbital is going to have a higher energy compared to the 1s atomic orbitals. And so that is a picture of how to understand the molecular orbital diagram, or the energy level diagrams for molecules. And so there's a couple of more things I want to talk about. So with regard to the 1s atomic orbitals interacting with each other constructively, you're going to form the sigma 1s. This has a stabilizing effect. This is a bonding orbital, and the bonding orbital has a stabilizing effect on the molecule. For this one, if they're forming destructively, or if they're interacting destructively, then you get this antibonding orbital. And antibonding orbitals have a disrupting effect, or another way to put it is has a destabilizing effect. So this is going to have a stabilizing effect for the molecule. So to form that bond, the bonding molecular orbitals are going to stabilize the bond between the atoms. The anti-bonding orbitals are going to have a destabilizing effect. And so what happens is, when you're adding electrons to the orbitals, the molecular orbitals, if you add them to a bonding molecular orbital, that's going to stabilize the bond between the atoms. If you add them to an anti-bonding molecular orbital, that's going to destabilize the bond. And mainly that's because you have a bonding orbital, the electrons are interacting with both nuclei at the same time. But for a antibonding orbital, you have a destabilizing effect. You have this node here, and so that's going to cause the electrons to interact with one nucleus at a time, not at the same time. So that has a destabilizing effect. And so we can see here that we can predict from the molecular orbital diagram that the hydrogen molecule is going to be stable, and it's going to form more readily than splitting it apart, because again, the two electrons that we have are going to fill up the bonding orbital, the sigma 1s bonding orbital, and therefore give the molecule stability. Compared to if you were to separate the atoms. The atoms being separate are going to be less stable than when they're together. So if you have two hydrogen atoms that are apart, they're going to come together really quickly, because that's going to be more stable, that's going to be less energy. So that's how you understand molecular orbital diagrams. I hope this was helpful. If it was, if you enjoyed the video, then please by all means like the video, share the video, hit that like button somewhere down here. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question about what I talked about in this video, or any other question, or if you have a problem you need the help with, put that down below. If you have a topic you would like me to cover, put that down below also. I would love to do that for you. Thanks for joining me and have a great day.